Hello, my name is Professor Brothers, and in this video, we are going to go over Bode plots. First off, what is the motivation behind a Bode plot? The idea is to provide an easy way to visualize the transfer function. This is done on a log-log scale, where we're going to compare decibels for the magnitude versus decades in frequency. This is an example of the Bode plot. On the top, we have the magnitude in decibels, and on the bottom, we have the phase of the transfer function. Let's go in and look a little bit about decibels first. Decibel is a ratio. It's a ratio between the output power and the input power. The generic equation for a decibel is 10 log P out divided by Pn. So given this, if P out is equal to Pn, we have 10 log of 1, that's going to be 0. So if we have an output of 0, such as on this plot, that's called the passband, where the output power and the input power are going to be equal. The signal is going to pass without any change in the signal. However, oftentimes for our transfer functions in ECE or electrical engineering, we want to compare the voltages. So H of S is often the output voltage compared to the input voltage. In order to get that, we need to convert this equation from power to voltage. We can use the substitution. Power is equal to V squared over R. If we do that, we can see in this equation now we have V out squared divided by R divided by V in squared divided by R. The two R's cancel, which is going to leave us with the squared term. So now we have V out divided by V in quantity squared. We can pull the squared outside of the logarithm, and that becomes a multiplication by 2, giving us now 20 log of V out divided by V in. This provides us with two equations for the decibel. The first equation in terms of power is 10 log P out divided by P in. The second equation in terms of voltage is 20 log V out divided by V in. We usually use the 20 log version for the transfer function H of S. Decibels, or now that we know about decibels, let's look at decade, the other axis. So decade is a way of plotting frequency in a logarithmic manner. If you look at this axis, you can see that we are going 0.01 rad per second, 0.1 rad per second, 1 rad per second, 10 rad per second, 100 rad per second. Each one of these spans is a decade. It's a multiply by 10. Another way that we can think about this, if we start on this end, we have 10 to the negative 2, 10 to the negative 1, 10 to the 0, 10 to the 1, 10 to the 2. So you can think about it in an exponential format in 10 raised to the power of. One of the interesting things about this is that you never reach 0. You're always one step closer to 0, but there's never a DC plotted on a Bode plot because you never get down to 0 rads per second. You're always one decade away from a smaller number. So when we do plots like this, another advantage of using decades is that you can very quickly compare megahertz, gigahertz, kilohertz. You can see a very wide spectrum of frequency responses on a single plot. So let's get into it. Let's look at a transfer function. Let's look at a generic transfer function. H of S is equal to K, which is some constant, S plus Z1, 0, 1, divided by S quantity S plus P1. The first thing we want to do, we want to convert this into a standard form. The standard form that we're going to use, we want to put this equal to K, and we want to factor out the Z1. K times Z1 times the quantity S divided by Z1 plus 1 divided by P1 S times S divided by P1 plus 1. What this does for us is it provides a ratio where we're looking at the ratio of S to the 0. So when S gets very large, this term is going to dominate over the value of 1. But as S gets very small, this term is insignificant compared to the constant value of 1. We're going to see why that's very important in order to create these Bode plots, because this provides us with a critical angle or a critical frequency in which we're going to change the direction of our Bode plot. We need to start with this standard form. Now, from here, the next thing we're going to do, we're going to make a substitution. We're going to say that S is equal to J omega. S is equal to J omega is going to put this in terms of only the Fourier transform domain. We're only going to look at the signal output of this, because that's where really what we want to understand is how the input signal relates to the output signal. All right, so with that, we can now transform this equation. We can say that H of J omega is going to be equal to K Z1 divided by P1 times the quantity J omega divided by Z1 plus 1 divided by J omega times J omega divided by P1 plus 1. Now that we have this, we're going to recall the equation to compare for an H of J omega into decibels. And we're going to use the voltage form of it. So we're going to use 20 log of V out divided by V in. But we actually don't want to look at the entirety of H of J omega. What we want to look at, the magnitude. We're going to split this up into first the magnitude and second the phase of the transfer function. We're going to look at them in two different plots. So let's look at the decibels of the magnitude of H of J omega. This means that we're going to get 20 log of the absolute value of H of J omega. That's what we want to get, the absolute value. Let me switch markers and see if there's a better marker to show up. All right, so 20 log of the absolute value of H of J omega. And then what we're going to do is we're going to apply that to the entirety of this function. And so this is going to be equal to, is that color better? I don't know. Let me try one more color. Hold on just a second. So that's going to be equal to, there we go. That one's a good color. That's going to be equal to 20 log of the absolute value of K Z1 divided by P1 times J omega divided by Z1 plus 1 divided by J omega times the quantity J omega divided by P1 plus 1. So this is what we're going to look at, the absolute value of this entire term. Now, this might look messy when we start out with it, but here's where the big simplification comes in. We can understand that one of the powerful things about a logarithm is that it takes a multiplication and it turns it into an addition. It takes a division and turns it into a subtraction. So that's where the real power of doing a Bode plot comes in. So now we can say that this all is going to be equal to, and we're going to start off with just this constant term, 20 log of the absolute value K Z1 divided by P1. That's going to be our first term. That's our constant term. That allows us to plot that term alone. We're going to add to that 20 log, excuse me, little typo, 20 log of this next term. We're going to look at the numerator of this term now. So 20 log of the absolute value of j omega divided by z1 plus 1 absolute value in parentheses. So that's the second term that we're going to examine when we do this Bode plot. The third term that we're going to examine is the standalone j omega in the denominator. But now that we're in the denominator, we're no longer going to do plus 20 log. We're going to do minus 20 log. And this is just going to be the absolute value of j omega. It's not the absolute value of 1 divided by j omega because we're getting rid of the division doing the subtraction. So it's just minus 20 log of j omega. And the last term that we're going to have in here is this last term that's in the denominator. And so we're going to do one more subtraction of 20 log of the absolute value. And again, it's not 1 divided by, it's just j omega divided by P1, the pole 1, plus 1 end. So in this way, we have now taken our transfer function and broken it up into a bunch of different terms. And one of the big things to notice about these terms is that they're very similar in structure. So if you look at this term, we have plus 20 log absolute value of j omega divided by z1 plus 1. This term, negative 20 log absolute value of j omega divided by P1 plus 1 in absolute value. We can now look at the building blocks of this equation and build it up in order to get the output. Okay, so let's go and look at what this looks like as we put it onto a plot. All right, so here's the equation that we came up with on the last PowerPoint slide. We have our 20 log of the absolute value of h of j omega is going to be equal to 20 log of this constant term. So this first term is purely a constant. The second term that we have going into it is the first 0. So it's got the plus 20. The third term that we have is the standalone s in the denominator, which comes out to be a negative because it's in the denominator, absolute value of j omega. The last term that we have is a negative because it's in the denominator again, j omega divided by the pole. What happens when we plot these? We're going to start out with the constant, and the constant value is literally going to be a constant over the entire duration of this plot. So what we do is calculate this value, calculate 20 log of this number. And when you do that, you're then going to plot it on the plot, and it will have some value. And I usually draw it as a dotted line across there. And then once we have this dotted line, we can add that to the other plots that we have in the diagram. The next thing we have is the 0, the numerator term, the 20 log. So the very powerful thing about the Bode plot is that we can use the plotting tools to not have to go into the details of what it is, but we look at where this ratio is equal and then starts to overcome. So depending on where the 0 is at, we're going to put a point where the 0 is at. And let's say, for instance, 0 is right here. The Z, let me make that a little bigger, I'm sorry. The Z1 term. Okay, so let's say Z1 is that omega value right here. This is the omega value that's going to turn this ratio into a unity, into a 1. What we do from there is now we plot 20 dBs per decade. This comes out of it being 20 log. So it's a positive 20 log. That's going to give us 20 decibels of gain over 1 decade of frequency. So we're going to look at wherever Z1 is, we're going to go 1 decade above there. And then we're going to look at the 20 dB line. And we're going to trace across the 20 dB line. And we're going to put another point. We're going to put that point right there. And that is 20 dBs per decade. And then we're going to come back and we're going to make an arrow connecting these. but it's going to be, the arrow is going to be bound at the lower Z1 value. I'm going to try to make this straight. And that arrow is going to continue going, but only continue going in the positive direction. It stops at the 0. And that's because at this point, the 1 becomes the dominant term. And the 1, if you recall from decibels, a 1 is 0 on the decibel scale. So this 1, the constant 1, is going to dominate this term. So it's going to go along until it hits Z1, and then it ramps up. So we can put in a constant at 0 dBs until it hits the value of Z1, and then it's going to ramp up. This is a bound term where the J omega divided by Z1 is insignificant until it passes and becomes greater than this fractional content. And at that point, it becomes the dominant term of the pair. But if we look at the denominator term, the negative 20 log of J omega, this is not bound. This is an unbound pole. So because of that, it does not have a starting point. It goes on forever in both directions. But where this one is positive 20 dB per decade, this term is going to be negative dB per decade. And if we think about this, this is actually going to be a J omega divided by 1. Divided by 1. So where this one started to cross the 0 axis at the Z value, this is going to cross at omega is equal to 1. So at omega is equal to 1, let's say that that is here right at this point. Omega is equal to 1. That's the point in which we're going to cross the 0 axis. And I'm going to change to a different color just to try to denote a little bit more. And so we're going to go 1 decade below, and we're going to go 20 dBs. And so we're going to start here at 20 dBs. Actually, that marker doesn't show up. Let me switch back to the green one. So we're going to make a point at 20 dBs at 1 decade below, and we're going to go 1 decade above and also go down to negative 20 dBs. And so these are our points that this line is going to go through, and it's going to be a straight line that is unbound. We're not going to have a knee in this line. It's going to continue forever in both directions. And I didn't use my straight edge, so it's kind of squirrely, but that's supposed to be a straight line. Pretend that that's a straight line. It has a slope of negative 20 dBs per decade. Okay, negative 20 dBs per decade. The last one that we have is another bound equation. This one, though, is bound at the value of P1, and it has the negative 20. So this one, again, we will have some value of P1. And let's say P1 is right here. Because, let me put that below the axis, show better. There's P1. And because we're going down again, this is in the denominator. So again, we have a negative 20 dBs per decade. So that is going to come across, and we're going to have that negative 20 dB per decade point right about there. I think that's about right. And so we're going to have an arrow that's going down at negative 20 dBs per decade. And before that, it's 0. It's 0 because the 1 is the dominant term in this pair. Okay, so that's how we start to do the plotting. We're going to break it all up. We're going to break it up into the constant term, the zeros, the unbound poles and zeros, and then the bound pole. All right, and in this way, once we complete this operation, we can add up these individual lines to get our overall Bode plot. We're going to do that in the next PowerPoint slide when I go through an example. But this is showing you the breakdown of these 3 or 4 different components. All right, so let's put all of this stuff together now. Here are the actual steps that we're going to follow in order to create a Bode plot. First step, find the transfer function. A lot of times this requires circuit analysis, simulation, measurements. Somehow you need to find the H of S transfer function. Step number 2, rewrite it in the standard form. Make sure that all of your poles and zeros are in the form of S divided by the 0 plus 1 or S divided by the pole plus 1. Doing it in this manner, we will make sure that the gain of the system is correct. Third thing you're going to do is going to be to sketch the magnitude, apply corrections, sum the lines, then connect the dots. You're going to repeat steps 3 through 6 for the angle plot. All right, so we're going to go through and look at these just a little bit more. But first, let's look at some material that I've provided for you on Canvas. If you go into the Files, Handouts, there's a folder called Bode. And inside that, there is a PDF called Bode Rules. And if you look at the rules for Bode plot, here's what you get. And it's kind of hard to see. I have it zoomed in on one of the other slides. But if you have a constant term out front, the way you calculate that is by taking 20 log of the constant term. If you have a real pole, it tells you how to deal with that. If you have a real zero, it tells you how to deal with that. One of the things we haven't talked about is a second order, a quadratic form, S to the squared. So here's the standard form for a quadratic pole or zero. And then the bullet points on how to deal with it for a magnitude plot and how to deal with it for a phase plot. So this is very handy. Make sure that you go and collect this so that you can use this as your guidebook for creating Bode plots. There's also the Bode corrections. This is one of the steps in creating the plot. Now, in general, we only are really worried about the corrections for the magnitude plot. For the angle plot, you kind of eyeball it and try to get the lines to be smooth. But for the magnitude plot, what you want to do is do a 3 decibel correction at the critical angles. You might say, well, what's a critical angle? If you think back on it, we had that Bode plot where we went along and then angled up at 20 dBs per decade at the 0. In order to do the correction for this, you would want to count up by 3 dBs at this knee. That's the critical angle. You count up by 3 dBs and you put a point there. If it is instead of a 0, if it is a pole that's going down at 20 dBs per decade, if it's 20 dBs per decade, you put a 3 dB correction point. So this is going to be 3 dBs. If it's a 0, it's 3 dBs above the line. If it's a pole, it's 3 dBs below the line. So either way, 3 dB correction. You want to do this on each of the individual terms. Then when you sum these lines together, you might have correction points that add together. But when you do this, you want to associate each one of the correction points with the summation term of the transfer function. All right, so that's how you do correction points. This is only for a first order. In order to do a correction point for a second order term, there's another handout. If you go back to the handouts folder, you can look for an undamped pole or an underdamped pole or an underdamped 0. This is the quadratic form, S to the squared. You want to put it into this standard form. And when you get it into this standard form, you can see there's a zeta in the S term, the second term, there's a zeta. If you look at this plot, it gives you the number of decibels correction on this axis based on all the different zeta values. So you reference this plot in order to calculate the number of decibels of correction. This also has a decibels of, or not decibels, a phase angle correction. But like I said, usually we're not as worried about the phase correction points. We really want to check the plot, make sure it looks right and looks smooth. But other than that, the main thing is to do the corrections on the magnitude plot. All right, so this is everything that I have for this presentation. There's going to be a couple more presentations that go through specific examples of how to create a Bode plot for both magnitude and phase. Thanks.